Hi guys, so let's do a quick recap of our introduction to momentum and impulse. So we began this chapter by considering a situation where there are bowling pins that are being struck by a bowling ball. Now we've already seen a situation like this. We could have calculated any particular variable, whether that's acceleration or delta x, using our equations from one-dimensional kinematics. We could have also gathered further information from using net force equals ma. And now in this chapter, we get introduced to yet another way to describe the motion and the change of motion, and that is by using momentum and impulse. So the first quantity that we were introduced to that was new to us was a quantity called momentum. Momentum is represented by the letter P. And again, this is the letter P, not a unit. So the first formula that we saw was P equals m times v, where m is mass and v is velocity. Since v is a vector, P is also a vector. So you should know that the quantity of momentum is a vector quantity. We identified the units of momentum as the product of the SI units for mass, which was kilograms, and the SI units for velocity, which is meters per second. And we also said that unfortunately, we do not have some nice package that represents a kilogram meter per second. For example, in work, where work had the units of a Newton meter became a joule. And for us, even though we have a kilogram meter per second, or its equivalent is also a Newton second, as the units for momentum, we do not have a nice simple unit to represent this quantity. So you'll have to just leave your units as kilogram meters per second. So let's consider another one-dimensional situation that shouldn't be too unfamiliar to us. Let's consider a box at rest. So again, this situation could be explained using one-dimensional kinematics, and it could also be explained using net force equals ma. And now using our new tool of P equals mv, we can find out some further information about our object. So consider this 1 kilogram box that begins at rest. There's an applied force that changes the velocity of the box. And after that force is applied, the box has a final velocity of 5 meters per second. Now remember that Aristotle thought that in order for something to be in motion, it needed to have a force constantly applied to it. And we know that that is not necessarily the case, that we can apply a force for a period of time, and that object to which the force was applied would continue to have a velocity even after the force was no longer on the object. So now we can take this information of mass, velocity initial, and velocity final, and we can figure out, well, how did momentum change? How much did it change by, and why did it change to begin with? Well, we can look at delta P, which is the change in momentum, as m times the change in v. Since mass will not necessarily fluctuate through our frame of reference, we know that the delta refers to the quantity velocity. Delta v is represented by vf minus vi, and distributing our m, we get delta p equals mvf minus mvi. So solving for delta p by plugging in our given quantities, we can see that delta p, or the change in momentum for this box, was 5 kilogram meters per second. Well, let's think about how that momentum was changed. So it is true that you don't need to have an applied force constantly acting on an object for that object to have a velocity. For example, if I push a bowling ball across the room, even after my hand has come off of the bowling ball would continue to have a velocity as it rolled to the other side. But how did I give that ball a velocity to begin with when it started at rest? Well, I did that in the same way that this person accelerated the box from rest. And the way that we did that was by applying a force for some arbitrary amount of time delta t. That quantity of F times delta t is called the impulse, represented by the letter J. So since force is a vector, impulse, J, is also a vector. Now remember again that the J is the symbol for impulse and not a unit. This is not a joule. This is the letter J that represents impulse. So we can generally say that a force applied to an object for a time delta t changes the momentum of the object. And we see that every day in action. If you are kicking a soccer ball, if you are moving something on a desk, or in the case when VF is 0, when you're bringing something to rest. Say somebody rolls a ball down a hill at you and you bring the ball to a stop. In the beginning of your packet, we start to ask some questions referencing Newton's second law of net force equals ma. And again, the reason that I have you guys go through these steps is so that you can see that these equations that we use actually come from other concepts and other equations. And that if you can make sense of something algebraically or via math, then you can make sense of something conceptually. So from Newton's second law, we start with net force equals ma. And we substitute in delta v over delta t for acceleration. And then we get the expression F equals m times the quantity delta v over delta t. Combining m with delta v and moving delta t to the left side of the equation so that it is now with force leads us to our very first theorem of this chapter. Dun, 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 dun. Behind curtain number 1, we see impulse momentum theorem. And so even though this is called impulse momentum theorem, I want you guys to remember that this theorem relates impulse to change in momentum. Okay, this is not impulse equals momentum. This is impulse equals change in momentum. Another way of expressing this theorem using the symbols that we just saw above is J, impulse, equals delta P, where delta P is m delta V. So what this basically says is that when you apply force to an object for some amount of time, you're going to change the velocity of that object. And that makes sense, right? We can wrap our heads around that. But taking that one step further, looking at the relationship between these variables and how they are related to one another on each side of the equation, we can deduce a further understanding of impulse momentum theorem. So some key points that build upon the fundamental understanding of impulse and momentum is that since F delta t equals m delta v, a very small force acting for a long period of time can change the momentum of an object just as much as a large force can acting for a short amount of time. Our next key point is that if delta V is negative, meaning VI is greater than VF, then force must be negative. And this you saw put into place during the first lab that we did of this chapter, which is the collision cart. Remember that all of the inputs in an equation need to be referencing the same object and the same frame of reference. So if we're talking about the change in velocity of something that's being brought to rest, we are not talking about the force on the object that is causing the other object to stop. We're talking about the force on the object that is stopping. And so that force would be negative. Our next key point, F and delta t are inversely related. They're being multiplied together on the same side of the equation. So if we hold m delta v constant, meaning we're not going to change the delta v, let's say that a ball is flying at me and it has some initial velocity that I have no control over. So someone across the room threw it at me and I'm going to stop this ball so that VF is 0. Then m, mass, and delta v are out of my control. I can't change those inputs in the equation. But if I don't want my hand to sting when I'm catching this ball, meaning I'm trying to minimize the force that I feel, and by Newton's third law, the force on the ball also, then I can do that by maximizing delta t. So this is what we saw in our water balloon toss activity, where you guys were catching the water balloons and you were bending your knees and you were trying to maximize delta t, or maximize the amount of time it took you to change the momentum of the water balloon so that the relevant force was minimized and the water balloon wouldn't pop. Thank you guys so much. I hope you're having a great weekend. Look for the notes on the homework on our website, and I will see you guys later. Bye.